We're going to continue on here to chapter 12, which is about bonding. So we're going to talk about bonding in this chapter. We're going to talk about really the two types of bonding. And really the two types of bonding that we're going to talk about is ionic bonding, which is always between a metal and a non-metal. And it's always the metal that is going to transfer an electron basically over to the metal. The result of that is we will make a cation that's positively charged and an anion, which is negatively charged. And there's absolutely the importance of this, no sharing of electrons here. So as we will talk about and we will see, what really holds this together is simply the positive and negative attraction between one another, the electrostatic attraction that's going to hold that together. The other type of bonding we'll talk about here is covalent bonding. And in covalent bonding, this is usually between two nonmetals. And as we talked about today, in terms of periodic trends, when we get two nonmetals together, they're basically located on the same spot pretty much on the periodic table, which means they share very similar periodic trends like electronegativity, ionization energy, and all those things that we were talking about today. So what happens when two nonmetals get together is they're not going to transfer electrons because frankly, they both want to hold on to their electrons and they both actually would like somebody else's electrons. So what happens is we end up with some type of sharing of electrons that happens in a covalent bond. And as we will talk about, sometimes that sharing may be equal sharing, sometimes that sharing may be unequal sharing, but there's some aspect of sharing that occurs in a covalent bond. And again, that is different than an ionic bond because in an ionic bond, we have a metal and a non-metal. And again, as we talked about with those periodic trends, metals are on the left, non-metals are on the far right there. They have very different sort of periodic trends where the metals, as we talked about, pretty much want to get rid of their electrons or lose them. And the non-metals want to accept the electrons. So we get a full transfer of electrons and it's held together by that sort of opposites attract. So the way that we oftentimes will represent bonding, both sort of covalent bonding and ionic bonding, is through the use of Lewis dot symbols. They're also sometimes just generically called electron dot symbols. And they basically are the symbol for the element. And we use one dot to represent each of the valence electrons. So we talked about today that the number of valence electrons equals the group number. And that's a really quick way, obviously, that you can figure out how many valence electrons somebody has. There's really no kind of big rule on Lewis dot symbols, except really that you usually don't put more than 2 dots per side. Which obviously, if there are 4 sides to a symbol, that's a grand total of how many dots? That is 8 dots. And as we talked about earlier, when we were talking about losing electrons and gaining electrons, that allows everybody to get to the magic number of 8, which is like our noble gases, which have 8 valence electrons. Remember that really the ultimate goal of bonding is for everybody to become isoelectronic with a noble gas, basically have the same electron configuration as the noble gas because they're very, very stable. And that's sort of the goal really of both types of bonding. Now, as I mentioned, Lewis dot symbol, 1 dot for each valence electron with an E instead of an A. Here's some examples of Lewis dot symbols. Again, you can see everybody in group 1 has 1, 2, 3, 4, 5, 6, 7, and 8. Again, a reminder that our helium here has only 2 because it has only 2 electrons total. The good news is we really don't deal too much with bonding and transition metals. Most people would consider transition metals to have 2 valence electrons, which is those S's we were talking about being lost. Some people might say they could have upwards of 12, depending on which one you're talking about, because we also go into the D's. But the good news is we don't deal too much with transition metals, so that's a good thing. So let's first talk about ionic compounds and covalent compounds. Again, as I mentioned, an ionic compound, always metal and non-metal. So it's pretty much as soon as you see that combination of elements, you should 100% of the time know that you're dealing with an ionic compound, which would be an ionic bond. And again, the positive negative attraction that's going to hold that together. Covalent is also sometimes referred to as molecular. Again, are two nonmetals with the sharing of electrons. So general rule tells us, as we sort of talked about, things with very low ionization energy, which means you don't need to put a lot of energy in there for them to lose electrons, will tend to form cations, which is again our metals, and our guys with high electron affinities, which again is the energy change that occurs when somebody gains an electron, will typically form our negatively charged anions. And again, those are going to be usually our nonmetals. All right. So let's take a look at an example of an ionic bond. So I have lithium, which is a metal, and I have fluoride here, which is fluorine, which is a nonmetal. So once I see these two combinations, I know this is going to be an ionic bond and an ionic compound that's going to happen. Now, if we do our Lewis dot symbol for lithium, lithium is group number 1 on the periodic table. And it would be lithium with a dot here. If we wrote the electron configuration 1s2, 2s1, that 1 dot is that valence electron right there. If we did fluorine or fluoride here, that would be group 7 on the periodic table, which means it should have 7 valence electrons around it. And if we wrote the electron configuration 1s2, 2s2, 2p5, I think. Now, what's going to happen in this case is, because lithium is a metal, and based on all those periodic trends we talked about, it's going to go, you could take my electron, no problem. And the fluorine, with all its sort of periodic trends, is going to say, thank you very much. I'm going to take your electron. That is the actual conversation. The result of that is lithium will now become positively 1 charged because it has lost an electron. The fluorine there will gain the electron. And as a result of that, the fluorine will now gain a negative charge. That's basically going to happen. And this is how we would represent basically this ionic bond being formed using Lewis dot symbols. A couple important things to note on this: because there is no sharing of electrons here with our ionic guy, we do need to include the charges on our picture there on the right. So we do need to put the plus there. We do need to put the negative there for the charges. And in most cases, somebody will kind of usually put a bracket around all of them or some of them. So I personally put a bracket around the negative guy, but sometimes you put a bracket around them to denote that there's absolutely no electrons being shared here. It is simply the positive and negative attraction that is basically holding those guys together. Now, let's take a look at what happens to the electron configuration on the right-hand side here. Once we have our guys with charges, when our lithium loses an electron, it's going to lose its valence electron here, which means that goes away, and lithium ends up with a 1s2 configuration. Who is 2 on the periodic table in terms of electrons? It is helium, and helium is a noble gas. So lithium here, by giving away its 1 electron, is able to achieve noble gas configuration as helium. Fluoride is going to take that 1 electron and basically add it right there because it has room in the p subshell. The p subshell at the beginning only has 5 electrons, so it has room to add 1 more to it. When it adds 1 more to it, we get 1s2, 2s2, 2p6. That is 10 electrons, are the same configuration as neon. So as I was talking about earlier, this is really the basis of all bonding here. In this case, lithium will give away its electron. It will allow it to back up to helium's configuration and become like helium in terms of its electrons and become very stable. The fluorine will gain the electron, and that will allow fluorine to go forward on the periodic table and reach the same electron configuration as neon. They both have now reached basically noble gas configuration in terms of their electrons, creating a very stable sort of bond But once again, there's no sharing of electrons. That positive negative attraction is what holds that together. Any questions on that there? All right. So that is an ionic bond. The electrostatic attraction is sometimes referred to as the positive and negative attraction between the different charges. A reminder that the attraction between things that are positive and things that are negative does increase with the number of the charge. So the greater the number of the charge, the stronger the attraction. So something with a +3 and a +3 and a -3 would be held tighter than something with a +1 and -1. Let's take a look at another example of an ionic bond. So this is calcium, which is a metal. And I'll try to write towards the top here. I know the visibility is not great here. Our oxide, which is oxygen, which is a non-metal. And once again, that's going to tell you that this is again going to form an ionic bond because we have those two things together. So if we take our calcium, which is group number 2, our calcium here should obviously have 2 valence electrons. If we do a little electron configuration there for our calcium, it would be argon 4s2, and these would be the 2 valence electrons there in calcium. Oxide is oxygen, which is group 6, which means it will have 6 valence electrons. And we do the configuration for oxygen 1s2, 2s2, and 2p4 there, I think. So same thing's going to happen here with calcium. It's going to decide I'm going to give away my electron, and oxygen is going to take 1. And it can also take both of its electrons basically over to oxygen. Now, why would calcium want to get rid of both of its electrons instead of just 1? If it gives away 1, it backs up to who on the periodic table? Only potassium, right? So it's got to give away actually both of those valence electrons to allow it to back up to a noble gas configuration and be stable. The result of that, again, is at this point, calcium will gain a +2 charge, and our oxygen will pick up those 2 electrons, completing its octet. And because it picked up 2 electrons, it will have a -2 charge in this case. And that means in terms of electron configuration for calcium with +2, it's going to get rid of those 2 electrons. And that brings our calcium to argon's configuration, which again is a noble gas configuration and really stable. Those 2 electrons that calcium lost can find a home right there in the 2p subshell. And that would give our oxygen here with a -2 charge, our oxide 1s2, 2s2, 2p6, which again is neon's configuration. So once again here, by losing and gaining electrons, both the metal and the non-metal was able to achieve noble gas configuration and become very stable. Our calcium backed up a couple of spots on the periodic table, and our oxygen went forward on the periodic table. Once again, there's no sharing of electrons here. +2, -2 is what is holding that together. Any questions on that there? Yes, sir. Yeah, there's really no rules. The only rule is no more than 2 per side. And most people a lot of times will kind of go single dot around them pair, but there's really no rule as long as you really don't have more than 2 per side is usually the main one. You don't. So here I'm just showing the electron configuration underneath it so that you could see that it basically has reached noble gas configuration by doing so. But if you were asked just to sort of draw the Lewis symbol through this, you can just draw the guys with the dots. So, same question or yeah. The first row has 6 dots because it has 6 valence electrons because it's group number 6. And it's actually these 6 right here. It's these guys right here. Those are the 6 that are in the highest energy level, and those would be where they would come from. Other questions? Okay. Now, what happens if we actually take a couple of those things together? What happens if we took our calcium here, which again had our argon 4s2, and our fluorine that we saw earlier, too many dots. There we go. Come back. All right. 2, 4. There we go. All right. So this has 1s2, 2s2, 2p5. So same thing is going to happen here. Our calcium is going to give away its electron over to our fluorine at this point. At this point, can that fluorine take any more electrons? No, it kind of just maxed out, right? It's able to kind of throw that one electron into there. And that's okay for fluorine, right? Because that's going to allow fluorine basically to reach the noble gas configuration. But as we just talked about, that's not going to be so great for calcium because it's only going to get to potassium. So in this particular case, calcium does need to sort of lose an extra electron. So we actually don't need just one fluorine, but we actually need 2 fluorines in this case. And that second fluorine now has sort of space for that second electron to basically go. And the result of this is calcium was able to get rid of both of its electrons, one to each of the fluorines. Each of the fluorines now will pick up an electron and become negatively charged. And each of these things, all 3 of these things, will now reach noble gas configuration. Our calcium gave away its 2 electrons, which means it has argon's configuration. Each of the fluorines individually just gained 1 electron, which allowed each of these fluorines basically to get to neon's configuration. So in this particular case, we actually need a little extra help there from an extra fluorine. And this is why, if you remember in an earlier chapter, we talked about when we put things together that are positive and negatively charged, the overall charge should equal 0, right? So when you take something that's positively charged and something that's negatively charged, they should add up to 0. And that's why calcium fluoride's correct formula is CaF2. We need 1 calcium, and we need 2 of the fluorines to do that. And the real reason why when we write a formula for an ionic compound that the charge needs to equal 0 is really this reason here. It allows every element there in that ionic compound, when you get it to 0 in the simplest way, to reach noble gas configuration. So that's really the reason why we balance out the charge to 0. It gets everybody to the noble gas configuration. Any questions on that there? Questions on how to show ionic bonding here. Okay. All right. Then let's move on to the other type of bonding, which is covalent bonding. And covalent bonding is a little bit different. So covalent bonding is always between 2 nonmetals, basically. And it is always sharing of electrons. So once again, because they are both nonmetals, they both pretty much want to hang on to their electrons and gain somebody else's electrons. As we will talk about here, it could be equal sharing or unequal sharing, but there's some aspect of sharing that occurs. So I'll redraw some of that stuff on the bottom with a little bit higher so it'll be easier to see. If we have a hydrogen and another hydrogen here, what's going to happen when they come together is, because they're both basically the same element, they're going to share those electrons between them. And that is going to make a bond there between the 2 where those electrons will count for both hydrogens. So for example, the hydrogen on the left gets to count the 2 electrons there in the middle, and our hydrogen on the right there also gets to count those 2 in the middle. And is that sharing of electrons that allows each hydrogen to basically end up with 2 electrons. Now, for hydrogen, that is perfect, because what element comes after hydrogen on the periodic table? Helium. And helium has 2 electrons. and helium is a noble gas. So hydrogen only needs to get to helium. So we'll take a moment here and talk about hydrogen. That means that hydrogen, for the most part, and every part, should basically only have one bond drawn to it. You could obviously draw the bond between the two hydrogen as a line as well. You should never, ever, ever, one more time, ever, yes, draw a hydrogen and start putting dots around it. Yes, because that's like a big X. Yes. Nor should you ever double bond, triple bond hydrogen and put dots around it. That's like a lot of big X's. Gonna kill all those things. So hydrogen should never ever have more than 2 electrons, which basically means hydrogen should always be on the outside, basically one bond to it, and that's it. It's done. You should never do anything other than that with hydrogen. I say that because I've seen like that last example there, like the triple bonded hydrogen and the dots all around. I think it looks more chemistry like that way. So don't do that. This is a covalent bond. This is sharing of electrons. The attraction of those negatively charged electrons in the center of those two atoms is going to be attracted to the nucleus of one and also attracted to the nucleus of the other. And that's what sort of locks those electrons into place. So once again, you can represent this bond by a line, which in this case would be a single bond, or you can represent it by 2 dots. So you can do it either way. I personally use lines for this type of bond, for a bond that's between 2 atoms, but if you like dots, you can use dots too. It's not wrong or anything like that. So in a covalent bond, again, that attraction between the negatively charged electrons and the positively charged nucleus in each case is really what holding that together. So again, here in covalent bonding, it is the sharing of electrons that's going to allow everybody to get to that noble gas configuration. So if we look at fluorine here and a couple of examples of fluorine, and again, I'll draw it a little bit higher so it might be easier to see. Fluorine again has 7 valence electrons, along with another fluorine here that has 7 valence electrons. So clearly they got the exact identical periodic trends, which means those two guys are going to end up sharing those electrons. And again, the result of that is you could represent it this way, or you could represent it this way with a line to show basically the bond that's happening there. And by doing this, once again, each of the fluorines in this case, get to count up all those electrons there, which are 8. And the fluorine on the right gets to do the same thing, count those guys in the center, giving both of the fluorines in this case basically 8 valence electrons, which once again is our noble gas sort of number. As you might imagine, 8 is a popular number here in bonding. It is what is referred to as the Octet Rule. It is, again, what everybody is striving to achieve, except for hydrogen. As we talked about, this should only obviously have 2. So when we look at a structure such as this, and again, I'll pop it up a little bit higher so it's easier to see. All the electrons that are not involved in bonding, so those are pretty much our dots here in this picture. Those all are what are referred to as lone pairs, if you're old like me. So these are what are referred to as lone pairs. They are most likely referred to nowadays as non-bonding electrons. Most books use that instead, non-bonding electrons. So if I say lone pairs or somebody says lone pairs, it's the same thing as non-bonding electrons. Those words are sort of used interchangeable. There's also the pair of electrons that are actually being shared between the 2 atoms, which is making a bond, and that is this pair of electrons. Those pair of electrons also have a very creative name, and the creative name is they're involved in a bond, so those are bonding electrons. So bonding electrons, much like the name implies, are involved in a bond between 2 atoms. And obviously lone pairs or non-bonding electrons are not involved in a bond. Any questions on that there? When you draw your Lewis structures, you should always include all of that. You should include the bonding and the non-bonding electrons. You should not leave any of those off. So a couple important things. Lewis structure, again, is a representation of basically covalent bonding, where we use dots or lines to show that bonding happening. It is important to remember that it is just the valence electrons, which should be an E, just the valence electrons that are involved here in bonding, and they are the only ones that are being showed. As we talked about earlier, there are still the core electrons, which are closer to the nucleus and not involved in bonding, but we just show really the valence electrons, which are involved in bonding. Here's another example, which is water. And again here, draw a little bit higher just to look at water. Water in this particular case here, the oxygen is sharing a pair of electrons with both hydrogens. So the oxygen there has 8 electrons around it. Again, each line represents 2 electrons, right? So we've got 2, 4, 6, 8 electrons. And it's the hydrogen sharing with the oxygen, which allows each of the hydrogen to get to 2 electrons. So once again, here in covalent bonding, the hydrogens and the oxygens are all sharing electrons, allowing all 3 of those elements the ability to get to the noble gas configuration. So as we talked about, that brings up the really important rule, which is the Octet Rule. The Octet Rule basically means that everybody will continue to make bonds until they got 8 valence electrons around them, except obviously hydrogen, which again, as we talked about, needs just 2 electrons. Hydrogen is sometimes referred to as the duet rule. It needs just 2 electrons, but the octet rule is pretty much everybody else. That is what everybody else needs to get to. Yes, sir.
There's also one important exception too. Boron is actually stable when it has 6 electrons.
It does. We're going to talk about that a little bit later on as well. There are some exceptions to the octet rule, which we will talk about a little bit later on in this chapter, but that is correct. Other questions? So talking about multiple bonds, when we do draw Lewis structures, now sometimes to get everybody to 8 valence electrons, you could do it just fine with single bonds. We'll get everybody to 8 valence electrons. So a single bond, once again, is 1 line or a pair of electrons or 2 dots. Now, sometimes it does require some double bonding to get everybody to 8 valence electrons. And a double bond is basically 2 lines or 2 pairs of electrons, or a total of 4. And that's what happens with CO2, which is on the bottom. So once again, I'll just sketch it up here so you can see it. The carbon in this particular case needs to actually double bond with the oxygen on both sides to get to 8 valence electrons. And the oxygen as well, by double bonding, gets to 8. And this oxygen also gets the 8 valence electrons. Now we also could have a triple bond, and sometimes you do need to get to a triple bond to get everybody to the octet rule or to meet the octet rule. And something like nitrogen is an example of that. Nitrogen actually is a triple bonded guy, and that gets everybody to the octet rule. So a triple bond is 3 lines, which represent basically 3 pairs of electrons or 6 total electrons. And again, nitrogen here by triple bonding is an example of something that will need to do that to get to 8 valence electrons. So this guy by triple bonding has 8 valence electrons, and this guy by triple bonding as well ends up with 8 valence electrons. Now, sometimes people want to always, when they draw Lewis structures for covalent bonding, which is what these things are, they always want to kind of maybe double bond or triple bond out of the box. And it's a good rule not to do that, even though you might think it looks more chemistry-like. But in a lot of cases, you really do want to kind of save double bonding or triple bonding to sort of fix an issue where somebody has not got to the octet rule. And we'll talk about sort of the order at which you can do that. The other example on the bottom there, which might be hard to see, is a triple bonded carbon with a hydrogen on each side. And once again, that sort of triple bonded oxygen able to get the 8, and this guy obviously here able to get the 8, and then our hydrogen able to get to 2, which makes it safe. So when we do share electrons, how do we know sort of, are the electrons going to be shared equally or unequally? And it is electronegativity that really is the factor that we look at when we try to determine whether or not we will share electrons equally. And a reminder, we just talked about it earlier today, electronegativity is the ability of an atom to bring electrons towards itself. And once again, in terms of the periodic table, it increases up to the right and decreases as you go down, with, once again, it is fluorine there. That is the most electronegative element that you could have. And if you think about it, that is pretty much as far up to the right on the periodic table as you could go, is fluorine. The only things to the right of fluorine are the noble gases, which are actually stable already. They're not really looking to do any type of bonding or anything like that. And that, again, why fluorine is the most electronegative atom. So electronegativity helps us distinguish between really covalent compounds and ionic compounds, although you really don't need it to determine an ionic compound or ionic bond. As you see a metal and a non-metal together, that's enough to know that it's ionic. You really don't need electronegativity values to help you determine that. But if we had something like hydrogen that we saw earlier, we would expect that these electrons here are going to be shared fairly equally with the hydrogen on the right. If my little lines here are the electrons being shared, and the hydrogen on the left, because again, they're basically the same element, which means they're going to pull those electrons pretty equally. And the same thing with our fluorine that we saw earlier, our F2. Each of those fluorines we would anticipate would share those electrons pretty equally, because it's kind of like two people pulling on a rope that's equally strong. Basically, the rope is not going to go anywhere, so they're going to kind of pull those electrons equally. We're going to get equal distribution of those electrons. This type of bonding here, where we end up with equal sharing of electrons, is what is referred to as a nonpolar covalent bond. Or most people very simply just call it a nonpolar bond. So a lot of times people will leave off the covalent because nonpolar would imply that the electrons are being shared as covalent. So nonpolar bond, nonpolar covalent bond is equal sharing of electrons. The consequence of equal sharing of electrons between two atoms is basically it's like a neutral bond, if you want to think about it that way. There's no side that's more positive. There's no side that's more negative. There's kind of just like nice equal sharing, and there's really no charge that's happening with that bond. Now, if we took something and swapped out, say, one of the hydrogens for the fluorine, now in terms of electronegativity, the fluorine is, again, the most electronegative atom there is, which means between the hydrogen and the fluorine, which one would be pulling the electrons closer to itself? It would be the fluorine, yeah? So what we're going to get in this case is, instead of equal sharing of those electrons, because fluorine is more electronegative, it is actually going to drag all those electrons towards itself, and a little bit of it's going to kind of hang out there by the hydrogen side. Now, there is also a consequence of this. The consequence of this is if all my electrons decide to hang out by the fluorine side, will the fluorine side of this bond be more or less negative? It should be more negative if the electrons are hanging out towards there, right? Electrons are negatively charged. And the result of this is it creates a partially negative charge, which is a delta symbol there, partial negative charge on the fluorine. And because the electrons are moving away from the hydrogens, it creates a partially positive charge on the hydrogen. This could also be represented by what is sometimes referred to as a dipole arrow, which looks something like this. And this type of arrow always points to the more negative or electronegative side. And the back part that kind of makes like a plus sign is to the side that's more positive. Now, what we get here is this unequal sharing of electrons. It creates these partially negative charge and partially positive charges. Why are they only partially positive and partially negative and not like a full positive charge and a full negative charge like we see in ionic compounds? The answer is they are still being shared. So even though they are not being shared equally, they haven't fully transferred from one to the next. Like the hydrogen is like barely hanging on, but he's still hanging on to them. So because they are still being shared, we don't get the complete transfer of charge like we get in an ionic compound. In the ionic compound, the electron fully transfers from the metal to the non-metal, resulting in a positive metal, a negative non-metal. In the case of a covalent bond like this, because it's still hanging on, it's still holding on to those electrons, we only create positive partial charges here. This type of bond here is what is referred to as a polar covalent bond, or just simply a polar bond. And that is basically unequal sharing of electrons. So in terms of covalent bonding, where we have sharing of electrons, there's actually two types of covalent bonding. There's one where we consider it equal sharing of electrons, which means it's a nonpolar bond and there's really no charge happening there. And there's a covalent bond where we have unequal sharing of electrons, and the result of that is a polar bond, and we end up with these partially positive side to the bond and partially negative side to the bond. Any questions on that there? And that's pretty much what this says. I drew a little bit higher. And again, so that represents, again, our polar covalent bond, or again, most people will just simply call it a polar bond. There's my smear, and that's my arrow that I drew up higher a second ago. So again, this is just what I just drew on the previous page. So to sort of summarize the three different types of bonding at this point that we've talked about, on one end of the extreme, you sort of have an ionic bond, which is always between a metal and a non-metal. And once again, you see that combination, that's all you need to know about it. It's going to be ionic. Again, we get the transfer of electrons. And again, that creates our cation, which is positively charged, attracted to our anion, which is negatively charged, and no sharing of electrons here. So an example of that would be something like sodium chloride is an example of an ionic bond. On the other end of the extreme, we have a nonpolar bond, our nonpolar covalent bond. That is between two nonmetals. Here we have sharing of electrons, and we have equal sharing of electrons. And an example of that would be like our F2 or H2 that we saw earlier. And sort of in the middle of those two is a polar bond or a polar covalent bond. And a polar bond, again, is between two nonmetals. Again, there is sharing of electrons. But this sharing here is unequal sharing. And obviously this right here is an example of it, HF, creating that partially negative charge and that partially positive charge. So again, one end of the extreme with ionic bonding, electrons completely transfer, they're completely lost, they're completely gained. You get full positive, negative ions that are formed. Other end, you got nice, perfect equal sharing of electron in a nonpolar bond. And in the middle, you don't have nice equal sharing of electron, but you don't have such unequal sharing of electrons that they've transferred. They're still hanging on, but it will create something with a charge, partial charges, because of that unequal sharing of electrons. Any questions on the three different types of bonding? Okay. So what helps us really determine whether or not we will kind of get equal sharing of electrons when we put two atoms together or elements together, or unequal sharing of electrons, is really the electronegativity. It also could help us determine ionic bonding as well. And electronegativity, as we talked about, is that ability to bring electrons towards itself. It's based on ionization energy and electron affinity. So fluorine has high electron affinity and a high ionization energy, which means it has high electronegativity. It likes to bring electrons towards itself. On the other end of the spectrum, on the left-hand side there, we have sodium, which has low electron affinity and low ionization energy, and has a low electronegativity. So a guy by the name of Pauling came up with a sort of scale for electronegativity that helps us determine if we take these two elements and put them together, would we expect it to share the electrons equally or unequally? His scale runs from 0 to 4, with 4 being the most electronegative and 0 being not so much. So in this case, yes, sir. I know there's an extra O. I know. Yep, there was. Thank you. So we use this scale here between 0 and 4. And 4 is the most electronegative, 0 is not so much. And we could use this to help us determine whether or not there is a equal sharing or unequal sharing by taking what is sometimes referred to as the difference in electronegativity, or the change in electronegativity. And basically what you do is you take the two values for each of the elements and you subtract the values. You can subtract them so you get a positive number. And if you do the difference in electronegativity, and it's anywhere from 0 to 0.4, that is considered a nonpolar bond, equal sharing of electrons. If you do the subtraction and it's like kind of 0.5, above 0.4 to below 2, that is considered a polar bond. And typically, if you're above 2, it is considered an ionic bond. The above 2 is not perfect. There are some ionic bonds that are actually less than 2. And again, that's what I was saying earlier. You really don't need the numbers for ionic bonds. You just need to know that it is a metal and a non-metal here. Hit the right button there. There you go. So let's take a look at that sort of scale. Here's a table of electronegativity values. You have a similar table, I think, in your book. Obviously, it would be provided for you if you needed it. But here's how we kind of can. So, for example, if we look at the ones we did before, we have something, say, like sodium chloride, which was an example of an ionic bond. If we look at sodium, its value is 0.9. Chlorine, its value is 3, I think. There we go. So the difference in electronegativity would simply be 3 minus 0.9. That is like a 2.1. That is over 2. And it would tell you that this bond is going to be ionic. Once again, truly, you don't need the numbers. As soon as you saw it's a metal and non-metal, it should be ionic. So you don't really need it. If we look at our F2, for example, that we did earlier, F is 4 and F is 4, which means the difference in electronegativity would be 4 minus 4, which is 0. And that definitely would be a nonpolar bond. Equal sharing of electrons would occur. When you actually take the difference in electronegativity and you hit a 0, sometimes people will call it a nonpolar bond, which it is. Sometimes people will call it a pure covalent bond. So if you hear the word pure covalent bond, it basically means a nonpolar bond where you got like perfect equal sharing of electrons. The reason there is sort of that distinction is you could go up to like 0.4 and it's still considered nonpolar, but in reality, it's not perfect equal sharing of electrons, right? It's going one way or the other, just slightly, but not enough to be considered unequal. But if you have a perfect 0 there difference, it definitely is considered nonpolar and sometimes referred to as a pure covalent bond. If we look at HF, which we also looked at before, H is 2.1, I believe, and F is 4. So the difference in electronegativity here is going to be 4 minus 2.1. That is a 1.9 difference. And that would tell us that this would be a polar bond. Yeah. 1.9 is pretty close to 2, where 2 is kind of our cutoff for ionic bonds and those electrons being transferred. So you can see there are degrees of unequal sharing, and this is pretty unequal sharing, but it's still hanging on, like I said, the hydrogen in this particular case. Any questions on how to use that there? So why don't you try a few? Why don't you determine, is it ionic, is it polar, or is it nonpolar for carbon, hydrogen? Let's do potassium and oxygen. Let us do carbon and oxygen. Let's do sulfur and oxygen. And let's do nitrogen and chlorine. For each of those bonds using the electronegativity values, I think I chose ones towards the top, hopefully. Determine, is it polar, nonpolar, or an ionic bond? Take a minute or two and determine. We're doing so again, we just want to take the difference and again do it so that you get a positive number. So we'll start with carbon, hydrogen. Again, I'll write it up a little bit higher so we can see it. Carbon here is 2.5 and hydrogen is 2.1, which gives us a 0.4 difference, right? When we subtract it, that would make it polar, nonpolar, ionic. It would make it nonpolar. The 0.4 is actually the cutoff for nonpolar. And it's really because of this bond here. That's pretty much what you find in organic compounds, like the heptane we used the other day. And most organic compounds are nonpolar. So the carbon hydrogen bond is considered nonpolar. And otherwise organic would be very different, I suppose. Coming out to our potassium and our oxygen. Honestly, at this point, potassium is a metal, oxygen is a non-metal, so it should be ionic. You actually don't really need the numbers to do this one. But potassium, if we did do the numbers, is 0.8. Oxygen there is 3.5. And that seems like a lot of math there, but is that like a 2.7 difference maybe? If I do that right. So that obviously is above 2, so that would be ionic. Once again, there are combinations of metals and non-metals that'll get you below 2, so it's not a really hard cutoff there. But once again, all you need to think about metal, non-metal, going to be ionic. We do carbon and oxygen. Carbon being 2.5, oxygen here being 3.5. So again, when we take the difference basically here, we are going to get a difference of 1. And 1 is obviously above 0.4, but below 2. So this should be a polar bond, unequal sharing of electrons happening. If we look at oxygen and sulfur, I'll go here maybe, oxygen and sulfur. Oxygen, once again, is 3.5. Sulfur there is 2.5. So once again, if we subtract the 2, we are going to get a difference of 1. And that again is above 0.4, which means that this bond here should also be polar, unequal sharing of electrons. And lastly here, nitrogen and chlorine. Nitrogen is 3. Chlorine is 3. That is a difference of 0, which means it is actually going to be nonpolar, equal sharing of electrons. It's also a good demonstration that you absolutely can have two different elements that will share the electrons equally. You for sure, if you have two of the same elements, they will share it equally, but you actually can have two different ones that can share it equally. The reason for that is what's sometimes referred to as the diagonal rule on the periodic table. Nitrogen is further up, but chlorine is further to the right, so they cancel out their differences. We also see that over here between carbon and sulfur, this sort of diagonal relationship that they end up with the same sort of electronegativity values. It's not usually the one right below it, but it's kind of down and to the right is that diagonal relationship. So you just got to watch a couple of those or a few of those that will end up with the same electronegativity value. Now, people always go, well, I can't answer these questions because I don't have a table. And you don't necessarily need the table in all situations to help you make an educated guess. You could use the general trend in electronegativity to do that. For example, we did carbon and oxygen. Carbon is right here. Oxygen is right here. They are in the same period on the periodic table. And the general trend for electronegativity is it increases as you go to the right on the periodic table, which means because the oxygen is further to the right, we should know that it's a pretty good guess that it will be unequal sharing of electrons. Oxygen will be more electronegative, and we would expect a polar bond to occur. We also could do that if we're comparing two things in the same group, which is like sulfur and oxygen, like we did. Oxygen is further up on the periodic table on the row there, and going up on the periodic table means electronegativity increases. So we would expect the oxygen to be more electronegative than the sulfur, and we can predict it to be a polar bond without the actual numbers. So if you're comparing something that's in the same row or something that's in the same group, you don't need the numbers. If they're opposites of each other or past each other, they will basically be a polar bond in most cases, and it'd be a pretty safe bet to just quickly figure that out. By the way, if we were to draw our dipole arrows, it should point to the one that is more electronegative. So in the case of carbon and oxygen, it should point towards the oxygen side. In the case of oxygen and sulfur, it should point towards the sulfur oxygen side in that case. And I think that was the only polar ones we had there. Any questions on how to use the electronegativity table or figure out polar or non-polar bonds? I personally say you should use this really just for polar and non-polar bonds if you really need to use it. But again, if it's in the same group or same row period, you don't really need the numbers. Any questions on any of that there? All right. So obviously, as we saw, atoms with very different electronegativity values, when we start mixing things to the left and to the right of the periodic table, we start to get ions being formed. And obviously in covalent bonding, where everybody's sitting in pretty much in the same spot for covalent bonding, all of our nonmetals are up there in the upper right of the periodic table, we're going to get sharing of electrons and covalent bonding occurring. So obviously a metal, non-metal ionic, two non-metals going to be covalent. All right, so that was basically the rule we talked about. Now, sometimes people will use this. I think there's a better table here, I think, yeah. Sometimes people will talk about percent ionic character. If something is 100% ionic character, it is a ionic bond. And obviously, if it is 0%, it is a nonpolar covalent bond or a pure covalent bond. As we see here as well, purely ionic, 100% ionic, 0%, and then obviously something in the middle there percentage-wise. All right, so now that we talked about bonding, how electrons are being shared, let's actually talk about how to draw Lewis structures for covalent compounds. And it's a little bit different than what we do for our ionic compounds. So this is really for, again, covalent compounds. The first rule up there, what it says is you want to think about sort of a logical arrangement of how the atoms come together. for the most part, the least electronegative atom should be in the center. And in a lot of cases, everything else is attached to it. So the least electronegative guy should be in the center. That eliminates fluorine from being in the center since it is the most electronegative. And as I mentioned with the never, ever, ever, that also eliminates hydrogen from being in the middle. Because if you put hydrogen in the middle, it's going to definitely have more than 2 electrons, which will not be good for hydrogen. Probably the most important thing for your picture is the next thing, which is you want to count up the total number of valence electrons in the molecule or ion that you are drawing. So remember that valence electrons equals the group number. You want to get like a total count, like my picture should have 24 valence electrons. And that number is really important because when you figure out that number and you draw your Lewis structure, you got to hit exactly that number on the nose. You can't have any more, you can't have any less. You got to be exactly there. Now, you will sometimes draw ions like polyatomic ions, which are nonmetals that are bonded together by sharing of electrons, but still has a charge. So anything with a charge, you need to adjust your total count of electrons. So if something has a positive charge, you need to subtract off the positive charge from your total count. And if something has a negative charge, it means it gained electrons. So you need to add the electrons to your count. Once you do that, what you really want to do is draw one single covalent bond between the center atom and each of the outside atoms. Remember that each line that you use represents 2 electrons. So that will take up a certain number of electrons from your total. So your total is say 24, you use a number of those electrons. You will still have electrons left at that point. Those electrons go on the outside atoms in pairs of dots until each of the outside atoms has 8 electrons. If you fill up all the outside atoms and you still have electrons, then you go to the center atom and you put them on as dots as well. Obviously, the only thing on the outside that should not have 8 again is hydrogen. Yeah, so no dots on hydrogen, but everybody else should have 8. At that point, you should be out of electrons. Otherwise, you miscounted. You should be out of electrons if you go to the center and you can put some dots on if you need to. The last thing that you want to do is check, did everybody meet the octet rule, which means everybody has 8 electrons, except for hydrogen that has 2. And it's at this point that if it does not meet the octet rule, you want to try to fix it by making a double bond. And you want to try to exhaust all your double bond options. And if it doesn't fix it with a double bond, then you would move to a triple bond at that point. So you kind of want to do it in that order. And that usually will give you a pretty good picture when you're all said and done. If you follow these rules, you should get a pretty good picture when you're done. If you do it by piecework, where a lot of people try to do, which what I mean by that is they go, well, nitrogen's got like 5 dots and this guy's got 6 dots, and you try to figure out where all the dots go and how they all bond together. Usually what will happen is you'll end up with a picture with not the right number of electrons, too many lines, that type of thing that happens. This should really get you to the right shot every time. So let's do one together to see how we've kind of put all those rules together. The first thing I'm going to do here with NF3 is I'm going to write it up here so we can go a little bit higher. There we go. So what I'm going to do is count up the total number of valence electrons. So nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which means they have 7 valence electrons. That is a grand total of 21 and 5, 26 valence electrons in this case. Now, in this case, I have 1 nitrogen and 3 fluorines. The most case, the nitrogen will be in the middle and 3 things will be attached to it. Nitrogen is less electronegative, obviously, than fluorine. So what I'm going to do is just arrange it that way. I'm going to have nitrogen in the center. I'm going to have a fluorine to the side, a fluorine to the side, and I'm just going to put a fluorine underneath it. Could you put the fluorine on top? The answer is yeah, you could have if you want to put it up on top. It doesn't really matter in this case. Now that I have my total number of valence electrons, I got my logical arrangement. I'm just going to lay up a single bond from the center to each of the outside atoms and make one single bonding electrons here in a bond. That is 3 lines. Each line represents 2 electrons. So that is 6 electrons I just put on my picture. That means I basically can subtract from my total here, and I got 20 more electrons to go. Those electrons are going to go on the outside atoms in pairs. So that is 2, that is 4, that is 6, that is 8, that is 10, that is 12, and that is filled because it now has 8 around it. That is 14, 16, and 18. And that guy is filled as well. I have now put on my picture 18 electrons. I believe 24 electrons would be a better count on that. I put on my picture so far 24 electrons. I still have 2 more to go. I filled up everything on the outside. Now I go to the center and I put it on as dots. At this point, I have now put up there 26 total electrons. I just need to make sure that everybody has 8, and then we will be good, and I think we are. So this fluorine has 2, 4, 6, 8. Every fluorine is identical, so they all have 8. The nitrogen has 2, 4, 6, and 8. So everybody has 8 valence electrons around them. That would be the correct Lewis structure there, outside of the highlighting, but that would be the correct Lewis structure for NF3. Any questions on those steps there? Okay, so why don't we try another one here? Why don't you try this one? Why don't you do NO3 minus and see what you come up? Okay, let's take a look, see how you're doing. So once again, I'm going to start with the total number of valence electrons. So we got a little NO3 minus. So we got 5 for the nitrogen. There's 3 oxygens. Each has 6 because oxygen's group 6. The negative charge here means I should add or subtract. We should add because it gained an electron. So that's going to be 18, 19, 24 valence electrons here. Once again, nitrogen is further to the left than oxygen in the same row, which means it's least electronegative. So we're going to put the nitrogen in the middle. We're going to do some oxygens around. And now we're going to do our bonding here. So we'll do 1, 2, and 3 bonds. That again is 6 electrons that we kind of took off our total. That's 18 more to go. Those again will go on the outside as pairs until everybody has 8. So that is 2, 4, 6, and that is filled. That is 8, 10, and 12. So that is filled. That is 14, 16 up on top, and 18 there on the bottom. I just maybe draw that a little bit better so it's easier to see. So I'll make it a little bit shorter. There you go. All right, at this point, I believe I have placed 24 electrons. That's my end here. Is everybody okay in this case? No, it is the nitrogen that is a little bit short, right? Nitrogen's got 2, 4, and 6 electrons only. The oxygens all have 8 electrons around it. So this is the point where we want to get ourselves to 8 electrons around the nitrogen. Can I just like put some dots there? I cannot, because now I have 26 electrons. So that's not good. So I can't do that. So this is the point where we want to make a double bond to try to fix it. We could actually make the double bond at any of the oxygens. Can I just, for example, draw a line here to make a double bond? The answer is no, for the same reason. I now have 26 electrons, and my oxygen has up on top 2, 4, 6, 8, 10, which is a little too much for the oxygen there up on top. So when we actually go to make a double bond or even a triple bond, what we're actually going to be doing is we're going to take a pair of electrons and we're going to actually bring them in to make the double bond. And when we do that, we will end up with a double bonded oxygen up on top, single bonded oxygens on the side there. And we will kind of put a little bracket around it to make it all chemistry like there, and a charge on the outside. And now by doing so, we have allowed everybody to reach the octet rule. Our oxygen here has 2, 4, 6, 8. This oxygen 2, 4, 6, 8. This oxygen 2, 4, 6, 8. And now our nitrogen has 2, 4, 6, and 8. So everybody has 8 electrons around it. And this would be the proper structure here for nitrate. Now, in this particular case, we had 3 equivalent oxygens, which meant that you really could have done the same thing to any of the oxygens. So for example, you could have double bonded to the right instead, and you would have ended up with something that looks like this. And you could have double bonded there to the left, where you would have ended up with something that looks like this. And all 3 of these structures are actually related to each other. They are what are referred to as resonance structures. And resonance structures occur in a situation like this, where you basically have more than one option to make the double bond with. And basically, it's because the double bond electrons are sometimes referred to as being delocalized. They are kind of like moving around. So at any point, they may be over here at the left, they may be up there at the top, they may be over there at the right. So they're sort of moving around. And the real structure is somewhere between all 3 of those. So we could draw more than one sort of structure to represent our resonance structure here. If you're not asked to draw a resonance structure, you don't have to draw all 3. Any one of the 3 pictures here would have been sufficient if you were asked just to simply draw a Lewis structure. So any one of the 3 would have been okay. But if you were asked to draw all the resonance structures,